Hey everyone, welcome to ECO 309 Economic Forecasting. In today's lecture, we're gonna go over chapter 3, Exploring Data Patterns and Introduction to Forecasting Techniques. First of all, I want to introduce time series data. I'm sure you may have some concepts about time series data. Basically, a time series is just data that are collected, recorded, or observed over time. For example, when we collect data on a company's revenue over time, then that is a time series data. If we collect the stock price for, let's say, for example, IBM over time, stock price over time, that's another time series, right? In economic forecasting, we mainly use time series data to forecast for future periods. But to determine what techniques we're gonna use, we need to first identify what type of data we are looking at. And typically we identify the data pattern based on the following 4 categories. The first one is horizontal data, type of data pattern. And when we have horizontal type of data, which I will show you really soon, we say that type of data is stationary. And sometimes we would observe trend in the data. That is, we observe the data is increasing over time or declining over time. Then those type of data are not stationary. We say it's non-stationary. There could be also seasonality, meaning that the same pattern up and down repeats itself within 1 year, and such pattern is consistent in terms from 1 year to the next. And finally, we have cyclical data, that is data is moving up and down along with the overall economic condition. We will go over all of these different patterns one by one. So we're gonna start with the first one, which we call stationary time series data. With stationary time series data, what we see is that the data fluctuate around a constant level. So for example, if you look at the picture I have here, you can see the data is going up and down, but briefly it is going around a constant average. I draw a blue line here roughly to represent the constant average. You can see the data deviates from this constant, but not far away, and we don't see any other pattern. We don't see any trend going up consistently or going down. We don't see the same pattern repeat itself over time. And therefore we say this type of data is, we say, stationary, okay? An example could be the monthly sales for a food product that do not increase or decrease constantly over time. And apparently this food product will be the one that is already in its mature stage, means it's not first introduced, it's not newly introduced. The demand for this product is constant. People's preference over this product is constant, so that the sales is not increasing or decreasing over time. The next ones we're gonna look at are the non-stationary time series data. And we do deal with such type of time series data more than the stationary one. A lot of times when we need to do the forecasting, and in order to apply the tools or apply the model we selected, we do need to change non-stationary data into stationary data, right? So for any non-stationary time series data, there could be 4 components. The time series could have all 4 components, or maybe just have 1 or 2 of them, all right? The first component is the linear trend, meaning the overall pattern of the data is going up or going down over time. And the second one is the cyclical component. Just as I said, this is the up and downs over long term based on the economy or some other conditions. The third one is seasonality, meaning that the data pattern going up and down repeat itself within 1 year and is constant from 1 year to the next. And the last one is called random error. This is kind of special. The random error does not show any specific pattern. It's completely random. It could be up and down. And actually, when you look at the stationary time series data, we can say that this time series data consists of random error that is going up and down, but it's not deviating from the constant mean, which is the blue line, consistently. So that's the random error. No pattern, no trend. You can't observe anything. You feel it's like it's going everywhere. That's the random error. Okay. First of all, linear trend. Okay. So the linear trend is basically describing the up and downs of the data over time, but it's not in a very short period. We're looking at the overall trend. It's the pattern of the data going up in general or going down in general. If you look at this right side picture here, okay, you can see, although there's fluctuation going up and down, the data is going up and down, there's fluctuation over time, but we can still tell that the overall pattern of the data is going up in general. So we call that, this straight line is kind of representing the overall trend of the data. We say we have a linear trend up there, okay? And actually in the real world, we do observe such trend for a lot of time series data, like population. We do expect population to grow steadily over time. Price, we do in general observe price going up, not dramatically, but still every year we do have certain inflation. We have for specific years, deflation means prices going down, but that's not common. Next, let's look at the cyclical components. So the cyclical component is basically the up and downs of the actual data around the linear trend. Okay, so let's go back to the same example we just looked at a moment ago. And the straight line in the middle apparently is the linear trend. So I'm just going through it. And you can see the actual data is going up at the beginning and then going down into a valley and then going up again. So this may reflect the economic cycle, or sometimes we call business cycle, meaning that the economy in the country or even over the whole world usually goes up and down, going up into a peak, and then the economy is going down slowly, sometimes even go into recession. Like in 2007 to 2009, we had the last major recession. It's really a severe one. And then the economy starts to recover for the next 6 to 10 years until right now, we basically can say the economy reached a peak. Some people may say, well, we just had another recession because of coronavirus. It is not completely confirmed. Typically, the Federal Reserve is the one to determine whether a recession has just happened or not. Regardless of that, so basically the cyclical trend or cyclical component, we say, is just the up and downs of the time series data due to the economic conditions. Okay, and for those of you who may be interested or curious to know, the economist has been for a long time trying to determine or trying to predict when we would have a recession, right? And what they do is they're trying to look for some indicators that can predict or tell us ahead of time that we are heading into a recession. And these are some of the leading indicators that they kind of find, including average weekly hours in the manufacturing, average weekly jobless claim. And I say kind of is because there's still argument going on as to what indicators really are, do they work? And it turns out actually sometimes indicator may work for this recession to predict or to tell ahead of time we'll have recession, and sometimes the leading indicator change to another one. All right. And next component we're going to talk about is the seasonality. So there might be times people are a little bit confused between cyclical component and seasonality because both of them are up and downs around the linear trend. So the cyclical component will be the up and downs over a long time. As you can see, this is for 20 years of data in the graph up there. So I don't have an arrow to use, therefore I use my highlighter a lot to kind of lead you to the point I'm talking about or show you the picture I want to point to, right? So for cyclical component, we're looking at a long term, over years. What we look at here is 20 years, and we see up and downs. And the up and downs can last 4 years. Now, in comparison for seasonality or seasonal component, the up and downs are within the same year. And we do see the same pattern to repeat itself year after year. What I have here is actually the quarterly revenue of Best Buy. And as you can see, there's up and downs, but such up and downs are within 1 year, and pattern is very repetitive. You can see the same pattern over years. And since this is quarterly data, that means every 4 points, 1, 2, 3, 4, that's 1 whole year. And for the next year, we have 1, 2, 3, 4. And the same pattern repeats itself every 4 quarters. Although in the middle, from 2011 and 2013, such pattern is not apparent, but afterwards we still observe the similar pattern, right? So we call this type of up and down the seasonality or seasonal component. I want to show you a kind of a comprehensive example in which you can tell there's 2 or more components showing up in one time series. And this is the KB Home's revenue data. KB Home is a home builder. What we can see here is, first of all, there's definitely some pattern. So we can tell the data is not stationary. Second, we observe this upward trend until 2006, and then going down all the way around 2011, then going up gradually again. So now we know there is at least some of other components. Now, visually examining the data, or what we call this, the graph here, we can tell there is definitely trend. There's also cyclical component because it's going up and down over long term. As to whether we have seasonal components, it's probably not very easy to identify, but what I can tell you later on, we'll see this clearly, is that we do have seasonality in this data. All right, that's visual examination. Actually, we do have a tool that helps us to confirm systematically whether we have any of the components or not. And that is the autocorrelation analysis, okay? First of all, what is autocorrelation? So the autocorrelation is slightly different from correlation itself. When we say correlation, typically we are referring to the relationship between 2 variables, and we label them as X and Y. For example, when we look at height and weight, we would expect that a person's height is related to, a person's weight is related to a person's height. The taller you are, the heavier you are, right? Then we say a person's height and weight is correlated. Now this autocorrelation still tells us the relationship, but it's not between two variables. It is actually within one variable. We're looking at the relationship between observation in one time period versus observation in another time period. Okay, so basically it is the correlation between a variable's lagged one or more time periods in itself. For example, if I'm looking at a company's revenue like KB Homes, right? I would expect that the current period revenue is related to the revenue in the previous period, right? Or by common sense, if I want to kind of predict without using any systematic tools, just a rough idea what my revenue will be for the next year, I would definitely look at my revenue this year. I'll probably even look at my revenue in the past couple of years. Why I'm doing that intuitively? Because I know the revenue in the next year is most likely to be somehow close to my revenue this year, and I do hope there's an increase. So in that sense, actually, the revenue in the future year is related to the revenue in the current year. And similarly, the revenue in current year will be related to the revenue in the previous year. And that kind of correlation is what we call the autocorrelation. It's the correlation between an observation in current period versus observation in previous periods. Okay, and autocorrelation can be used to identify patterns such as trend and seasonality. Unfortunately, it cannot be used to identify cyclical trend. And we use R with a subscript K to denote the autocorrelation coefficient. And this K denotes the lag. What do we mean by lag? The lag means how many periods you want to go back. For example, if I'm looking at K equal to 1, that means the autocorrelation is denoted by R1, and that is referring to the correlation between values in current period versus value 1 period ago. Okay, if I'm looking at K equal to 3, then the autocorrelation will be denoted by R3. And then I'm looking at values in current period versus the value 3 period ago. We typically calculate the autocorrelation, put it into graph or get the numbers to further identify if we have any trend or seasonality. So I want to go through an example and show you how we get the autocorrelation and how we can read the results. So this is data on the number of VCRs sold last year by Verna's music store. It's apparently very old data because maybe some of the young generation don't even know what VCRs are. It's been a long time ago. Even after VCR, we had CD, DVD, Blu-ray, until right now, I believe a lot of people are streaming online. But anyway, so we have 12 observations, as you can tell, you can see from the table right here. Okay, and I can tell it's time series data because it collected over the 12th month in a year. We're gonna move now to Minitab because I want to show you there how to obtain the autocorrelation values and also how to obtain the ACF graph. Then we'll go from there. So let me switch to my Minitab. It is also highly recommended that you carry out the analysis in your Minitab while going over the lecture. So if you haven't done so, maybe you want to pause and obtain the data from D2L. I post all data used in our course on D2L, you can find this under week 1. And the name of the file should be VCRs. It is already a Minitab file. You can open your Minitab directly. You don't need to go to Excel to do anything else. So I open the file now, and you can see there are 3 columns. First column is time, second column is month, and the third column is the actual data, the actual number of VCRs sold. Okay, for this task, we want to obtain the autocorrelation graph and autocorrelation numbers, values. So what we do is we go to stat on the top, and then you move to time series. We'll be using this a lot. Then going through the list, you will find autocorrelation. That's the one we want. So click on it, and you will see a pop-up window. On the pop-up window for the series, basically we need to tell Minitab where our data are. And the data we're gonna use is really the third column called data. You can pick the number of flags. Typically, we can just leave it like the default number of flags, but you can also specify it. Let's just click on OK and see what happens. Okay, so first of all, on the top, in this box, you see these are the autocorrelations for the first 3 lag. Okay, and the reason that Minitab only provides 3 lags is really because our data is very small. We only have 10 observations. You do need to have enough observation to go upper in the lag. And therefore, if we look at the next one, it is the graph for the autocorrelation function. You see these 3 autocorrelations are represented by the blue bars. Okay, and the blue bars are decreasing. For the first lag, the blue bar is around 0.6, and for the second one, for lag 2, it's around 0.5, and for the third lag, it's around 0.1. All right, so that's the autocorrelation. What does it tell us? Well, it tells me for VCR sales in the data, value in current period is slightly correlated with value in the previous period, but such correlation is decreasing quickly when we get to the correlation between current period value versus 3 periods ago. They are almost not correlated at all. Okay, so that's, as of right now, what we can see from the autocorrelation graph. Okay, so let's return to our PowerPoint slides. And so far in Minitab, we've been able to obtain the results as I shown here. All right, and I briefly explained what we can tell when looking at the Minitab output. Once again, here are some of the details of what I just said. For leg 1, the autocorrelation is 0.57. And that means the current month sales of VCR are somewhat possibly related to sales 1 period ago. It's not very strong because it's not very close to 1. The closer the value is to 1, the stronger the autocorrelation will be. It's similar to the correlation coefficient. For leg 2, the autocorrelation is 0.46. We can say there's still positive and moderate relation between current month sales and sales 2 periods ago. However, as we move to leg 3, right? When we look to move to leg 3, we can see that such autocorrelation almost disappeared. The value is only 0.11. That means current month sales are virtually not correlated with sales 3 periods ago. And the next concept I want to introduce is to actually determine whether the autocorrelation we observe exists or not. Statistically, we need to look at the significance of autocorrelation coefficients. And this is related to part of the review in chapter 2. We are going to look at hypothesis test. What we're testing on. So we're testing to see whether the autocorrelation coefficient we observed in the data really means there's actual autocorrelation in the whole population. Like for this example, we had 12, I'm sorry. I made a huge mistake so far, but correct myself, 12 observations, because there are 12 months in the year. So in this example, we have 12 observations. And from the data, we observe the following autocorrelation coefficient. But what we're asking for all sales for the store, for all VCR sales for the store over the whole time period, can we still claim there's autocorrelation for leg 1, leg 2, etc.? And to determine that, we will need to test on the autocorrelation coefficient, which is denoted by rho for the population. I know this is another notation for autocorrelation coefficient, but this rho is representing the coefficient for the whole population, not just the 12 observations we see in the data. And we're asking whether such autocorrelation coefficient is equal to 0, meaning there's no correlation, or it is different from 0, meaning that current period value is related to value in previous periods, okay? We will not go through the whole hypothesis test by looking at the test statistics and everything. What we do is that we're gonna briefly look at that. And because the output from Minitab does not provide us with the p-value, instead it only provides with the test statistic. If we want to make a decision, we have to rely on what we skipped during the review, the reject region approach. But don't worry, we have a rule of thumb that can help you to get a general idea about what decision we can make using just the t-test statistic. And we also have an alternative way to determine whether we're gonna reject them or not. Or we can tell whether such autocorrelation for the whole population exists or not. So the rule of thumb is the following. When we look at the t-test statistic, the threshold we can use is 2. That's the magic number. If our test statistic is greater than 2, this t-value is greater than 2, then we can say we're gonna reject the null hypothesis and conclude that such autocorrelation exists for the population. If the t-value is less than 2, like what we have here, 1.96, then we will say such autocorrelation, although identified in the sample data, actually does not exist for the population. Okay? And if we look at leg 2, that t-test is even smaller, 1.25. So we can definitely tell for the population, such autocorrelation observed in the sample actually is not true or is not significant. Actually, significant is the term that we should be using in statistics. And it's a common term that for people know statistics, they all know the meaning of the significance. Basically, that just tells us when a test is significant, then the null is rejected. Okay, and therefore, just based on the t-test statistic, 1.92, 1.98, and 1.25, we can tell for the first 2 legs, the autocorrelation coefficient is not significant, and therefore there's no such autocorrelation in the population, although we do observe some autocorrelation in the sample data. okay? The rule of thumb, again, is the magic number 2. So the alternative way to determine if the autocorrelation coefficient for the population is significant or not is to look at another approach we reviewed in chapter 2, which is the confidence interval. Well, in the output from Minitab, if you look at the graph right here, you do notice that there are 2 red lines, one on the top and one at the bottom. Those 2 red curves or lines are actually the confidence interval. And the idea here is this is the confidence interval for the autocorrelation coefficient. And if the blue bar, the blue spike, is outside the red curve, then that means the autocorrelation coefficient is significant. Or it is, we can say it's significantly different from 0, and therefore such autocorrelation exists for the population. Okay? So again, the red curves are the confidence interval for the autocorrelation coefficient. And whenever the sample autocorrelation coefficient exceeds such confidence interval, we can say the autocorrelation coefficient for the population is significant or significantly different from 0, and therefore such autocorrelation exists for the population. Now, apparently for our example here, all 3 legs are within the confidence interval, and therefore none of them are significant. So basically what we can say is for this VCR sales data, there's really autocorrelation for the first leg, the second leg, the third leg is not significant enough for us to conclude that the current period value is related to any of the previous period value. And of course, one potential reason could be that our sample size is so small. But that's what we can conclude from the sample data. Okay. Now, after introducing the basic idea of significance and testing of autocorrelation coefficient, we can use it to make judgment. Okay, and we need to know the pattern we're looking for to determine whether our data have trend, seasonal component, or our data is just stationary. In other words, random. So for stationary data, that means there's no autocorrelation, and that means the data are just random. We would expect that all autocorrelation lie within the interval, or in other words, all the blue spikes are within the red curves graphically, right? All the blue spikes are within the red curve. That means our data is stationary and there's no autocorrelation. If there's trend, what do we observe? Well, we will observe that the autocorrelation coefficient are significant for the first several time lags and then gradually decrease towards 0. Now, graphically, that means for the first several lags, the blue spikes will exceed the red curves. And I'm going to show you a graph really soon. And then the blue spikes will decrease gradually towards 0. Now, thirdly, if there's seasonality, then we would observe that the autocorrelation will be significant and actually very significant as the seasonal time lag. Okay, or in other words, that blue spike at the seasonal time lag will be very high, higher than the previous one, higher than the one afterwards, and also exceed the red curves, exceed the confidence interval. And such seasonal time lag is usually 4 or 12, because if you have quarterly data, then the data repeats itself every 4 periods, and you would observe that current period value to be highly correlated with value 4 periods ago. That is, my first quarter data will be correlated with the first quarter data in the previous years. Okay, and if you have monthly data, then you would expect such seasonal time lag will be 12 because there are 12 months in the year, and you would expect the value in this year's, the value in January of this year is highly correlated with value in January in the previous years. Okay, and that's why for seasonal, the seasonal time lag will be usually be 4 for quarterly data and 12 for monthly data. Okay, so let's look at several examples to help you to identify what kind of autocorrelation graph indicates stationary data, what kind of ACF autocorrelation graph indicates trend and seasonality. And by the way, so autocorrelation function is also called ACF, just to be simple. And we call this type of graph ACF graph. Okay. All right. So here is the first example, and we did it on purpose. We used Minitab to generate 40 random numbers, and we know they are random. So we don't expect any pattern. We don't expect trend or seasonality, cyclical, anything other than just randomness, okay? And in the first graph, you see that's the plot of the data showing us the value of each data. And it's going up and down, but it's still around a constant mean. It's not deviating substantially as a trend with the trend. Then we can upturn the autocorrelation with t-test statistic and also the graph. So let's move to Minitab again, and I want to show you again how to get this. You may already be able to do it, but it doesn't hurt to, for practice purpose, to do this one more time. So let's move to Minitab and want to show you how to get the time series plot and also the ACF graph. And here's the data. The name of the file is called pseudo-random data. And you will see 2 columns. The first column identifies the time starting from 1, 2, 3, and 240. The second column is the actual value of the data. Now for time series plot, you can either go to graph and find time series plot option towards the bottom, or you can go to stat and time series, and then you'll find time series plot as the first option. Okay, so either way will lead you to the same destination. I'm gonna just click on time series plot. We will use the simple one always. For our course, we don't need the other ones for more complicated situations. So click on OK. And if this is the first time you are doing the time series plot, you will see series box is empty, and you want to identify the value as YT. When you double click on it, YT will be filled into the box automatically. And then click on OK. You will see the same time series plot we just saw on the PowerPoint slide. Again, it's purely random, up and down. We don't see any patterns. Next, let's do the autocorrelation graph. So still go back to stat, time series, and then click on autocorrelation. Again, if this is the first time you're doing this, the box for series will be empty. Just double click on YT, our data. That will be filled into the box directly. We will still use the default number of lags. That should be sufficient for us to make a decision. So let's click on OK. And on the top, you will see the autocorrelation coefficient together with the test statistic T. Now this T is different from the one we just had because you would notice that some of the ACFs are negative and correspondingly the T's are negative too. For negative T's, instead of comparing with 2, we want to compare with negative 2. And the rule of thumb now becomes if this T is less than negative 2, then we're gonna reject the null hypothesis and say the autocorrelation is significant. Okay, so for example, if it's negative 2.5, then we're gonna reject the null and say the autocorrelation is significant. Apparently for our example here, none of the T's for the negative ones are negative, are less than negative 2. So we can tell right away that none of the autocorrelation coefficient are significant. Further, let's move to the graph. Visually, it's easier for us to identify that for all the autocorrelation represented by the blue spikes, they're all within the red curves. So none of them are significant, which confirms that our data is random. We don't observe any pattern. Okay, or in other words, we can say our data is stationary. That's another term we can use. So let's move back to the PowerPoint and look at another test. This is the Q-test, Lombok's Q-test. So this test is slightly different from the t-test, but the purpose still for us to determine whether the autocorrelations are significant or not. The idea of this Lombok's Q-test is to ask, although each individual autocorrelations are not significant, but what if we combine them and look at them comprehensively? Okay, let's say we want to look at the first 10 legs. And then test to see if for the first 10 autocorrelations, are they significant or not. We don't use T or Z distributions. We actually use a new distribution called chi-square distribution. And I do not intend to spend more time talking about this new distribution. Just instead say, well, for the new distribution, it is not bell-shaped, it's not symmetric, and it's not similar to T or Z that we reviewed in chapter 2. And for the Lombok's Q-test, we don't have p-value either. We will have to rely on the reject region. And the rule of thumb, not a value, the rule of thumb is that for this test statistic, for the LBQ, you will see in the last column, okay? The higher the number, the more reason for us to conclude that as a group, the autocorrelation coefficient is significant. And for our example here, if we look at the first 10 legs, the test statistic is 7.75. And if we compare with the threshold, that's not high enough to say that the autocorrelations are significant. Okay. So next, let's look at what we can see if there's trend. So in this example, we have an analyst for Sears, Maggie. She is assigned to the task of forecasting operating revenue for 2005. Then she gathered the data for years 1955 to 2004. Same as before, we obtained the time series plot, we obtained other correlations from Minitab, and we look at the graph to determine what's going on there, okay? And do not intend to go back to Minitab. You can do this as practice yourself. Basically, the steps are the same as before. And therefore, let's jump to this time series plot right away. So these are yearly data. and therefore we won't observe seasonality. We do observe a trend though, that is before around 1992, we see upward trend. However, after 1992, we see downward trend. Now next, moving to autocorrelations, all right? Look at the T's. If we compare that with 2, right? For the first 4, we can definitely tell the autocorrelations are significant, meaning current peak value is highly correlated with values in the past 4 periods, okay? If you look at LBQ, recall that we tested for the first 10 lags in the previous example, and the value is around 7. Now for this one, for the series, if you look at first 10, the value is 300. Very big. So apparently there is autocorrelation. But that's not enough for us to say, oh, there's a trend. What can we say? Well, when you move to the autocorrelation graph, okay, what you will see is that first 4 spikes, the blue spikes, exceed the red curve on the top. And therefore, those 4 are significant. Also, we can observe that the spikes are decreasing gradually over time, gradually and slowly. So this kind of pattern will allow us to conclude that there's trend. Okay, again, 2 things. Number 1, for the first couple of lags, the autocorrelations are significant. Number 2, the autocorrelation is decreasing gradually. These 2 features will allow us to say there is trend. Okay, now it doesn't have to be the first 4. It could be the first 3, it could be the first 6. That's what we are looking for in terms of determining whether there's trend or not. All right, seasonal data. How do we determine if there's seasonality? Okay, so here's another example. So Perkin Kendall is an analyst for the Coastal Marine Corporation. He gathers the data for the quarterly sales of the Coastal Marine Corporation from 1994 to 2006 and plots them as the time series graph. And we want to know if there's seasonality or not, because we know this quarterly data, there might be, right? So the first table shows you, the table on the left shows you the actual data, and if you go to mini tab, so the table, on the left shows the actual data, and the graph in the middle is the time series plot of the sales. We can observe certain patterns. We can see from first quarter it's going up, the third quarter is a peak, and then fourth quarter is going down a little bit. And then repeat itself every year. So even from the time series plot, we do observe seasonality. The same pattern repeats itself every 4 quarters or every year, okay? Now you will notice that at the bottom, for the time series plot, I did put the year and the quarter there so that I can kind of identify which year, which quarter. In Minitab, there is a way to do that. So I put the pop-up window there just to let you know how we can obtain the x-axis notation. I'll show you in a minute. All right. So next, let's examine the autocorrelation graph. And Here's the Minitab output. What you would observe is that if you look at the spikes or the autocorrelation represented by the spikes, for the fourth leg, right, it is very strong. The fourth leg exceeds the red curve, okay? It is also much higher than the previous one and the one after it, leg 3 and leg 5, telling us the observation in current period is highly correlated with the observation 4 period ago. That's exactly the same quarter in a different year. And therefore, from this, we can tell that we have seasonality in the data, okay? So again, the feature we're gonna look for to identify seasonality in the autocorrelation graph is that at the seasonal lag, which is 4 in our example because of quarterly data, we would observe significant autocorrelation. Also, this autocorrelation is greater than the autocorrelation in the previous lag and also in the next lag. Then we can tell there is seasonality. All right. Before I move to KB Home's data again, I want to actually go back to Minitab and quickly show you how to obtain the x-axis notation. So going back. So the name of the data file is Coast Guard Marine Chapter 3. Okay, I've already put it up. The first column is the time. The second column is the actual sales. And we want to create a time series plot with labels for the x-axis. So we're gonna go to Stat, Time Series, click on Time Series Plot, and we'll pick Simple. The series will be sales, and we want to click on Time/Scale, okay? Once you click on it, you will see this pop-up window. We want to pick Stamp, and the stamp is just the label for the x-axis, and the label is provided in time. That's the variable. So we want to double click on it, then click OK, and OK again. Okay, then there we go. We've got the time series plot with the labels for the x-axis. All right, now let's move on back to our PowerPoint slide and continue with the KB Homes data, right? We looked at this time series plot a while ago, and I briefly talked about the first impression by looking at the time series plot. Now we can use the ACF to determine whether there's trend, there's seasonality, okay? So on this page, I provided the Minitab output for the autocorrelation coefficient table and also the ACF graph. All right, first of all, it is very easy to tell there's strong trend because for the first 1, 2, 3, 4, 5, 6 lags, they're all significant. The spikes are all higher than the red curve, meaning they are significant. And we also observe that the autocorrelation is decreasing gradually into negative. Okay. Next thing we want to identify is about the seasonality, right? Since we are looking at quarterly data, we know the seasonal time lag will be 4. So we should focus on lag 4, which is this guy right here. Okay, first of all, at lag 4, autocorrelation is significant. Second, you can also see that this autocorrelation is greater than the one in leg 3 and also greater than the one in leg 5, indicating that we do have seasonality. In addition, since for this example, we have 24 legs, you can even go to leg 8, this guy here, okay? It is not really significant, but it is still much higher than the next leg. And it's almost the same as the previous one, okay? And if you go to number 12, right here, same thing, much higher than leg 13, but it's about the same as leg 11. And therefore, we can tell from these legs, there is seasonality in the data. All right, so that's the end of this chapter. Let me know if you have any questions. Send me an email if you need help. Otherwise, I will see you next time.